So today we'll compute the Gaussian width of certain like more abstract sets. So the idea will be that let's say that we have some signals of interest, right? Some S, we're interested in measuring X, some signal of interest that belongs in some set. Okay, maybe I won't use the same letter S. Let's say it belongs in some set T, right? Maybe T is the set of all natural images, or the set of all possible brain scans output of an MRI machine, say, or things of this type. Then we might want to measure X, right? We might want to do some kind of measurement of the form, say, AX, right? Maybe we're taking linear measurements like yi equals AI transpose X, right? And we take many of these measurements. Let's say that X is a vector. Okay, here, our vectors ambient dimension before was D. Here we use N as it's more common in signal processing. And let's say we take a lot less measurements, right? That would be the idea. We take only M measurements. Right now, if we take these to be random, then really, I mean, all we're doing is we're taking a linear, right? We're taking a linear measurement. We're multiplying X by a matrix A, where A has these vectors, right, posed here. Now, if we take them to be Gaussian, right, so A is a matrix that's Rm by N, right? And if we take it to be Gaussian, then we could ask, well, how many dimensions M do I need in order to preserve the norm of all the vectors X? Now you might ask, okay, why do you care about preserving all the norm of the vector X? Well, maybe we don't care so much about preserving the norm of the vector X's, but maybe we care about preserving distances between the vector X's. Because if my measurements, I can do it with a lot less number of measurements, and still any two vectors in the set that I care about, T, if they're far away in ambient space, they're still far away after measurements, then this is a good sign, right? I mean, if I have something like A of say X1 minus X2, right? If this is bigger than 0 and a lot bigger than 0, then if this is equal to something that's also a lot bigger than 0 by norm, it means that if the thing I'm measuring, right, if I could measure two things and they're very different, then my output is also different. It means that if I measure something, there's nothing else possible. There's no, let's say, if I take a picture of a like I take a picture of a scene, right? So I have a natural image. If I know that my way of taking pictures, right, let's say I use something like this, is so that, you know, if two pictures are different, the measurements will also be different, right? And so this means that potentially you can take pictures with a lot less measurements than the number of pixels, right? Potentially you can take them, say, with Gaussian linear combinations of pixels and get away with a lot less. And indeed, this is sort of at the heart of the idea behind compressed sensing and the so-called one pixel camera. And this is particularly important for, say, when you're doing MRIs, for example, because less measurements means that the person needs to be less time in the machine, right? And this could actually be not only because it's sort of inconvenient to be in the machine, but there's many cases in which it's really critical to make this time as little as possible. Like when you have to take pictures and say you have to stop some organ from moving, like the heart or something like this, then it's very important. So the goal here, I mean, we're gonna give a few lectures on compressed sensing further on, but now I just want to describe how we can use Gordon's theorem to sort of understand how many measurements we need, right? Because if we think of our measurements as random Gaussians, right, just kind of random Gaussian vectors, then it really is about how many dimensions do I need in order to keep the norms of the set of differences, right? The interesting set S will be the set of what we call T minus T, right? The set of all x1 minus x2, where both x1 and x2 are in T. Right, and now basically the M that I will need, it will depend on because of Gordon's theorem, we'll need to understand the Gaussian width of the set S. Okay? Now, turns out that natural images and in some sense the brain scans and so on, they tend to be sparse in a certain basis, right? So we'll talk more about this when we talk about compressed sensing. But it turns out that a set of interest is the set of sparse vectors. Okay, so the set of S sparse vectors. Okay, so we're going to call something the L0 norm, even though it isn't really a norm, because well, first I'll define it, right? This will be the number of non-zero entries of X. Okay, and we'll call this, we'll call this set the SS. Will be the set of S sparse vectors that have norm 1. Okay, so let me define it here properly. All right, so why isn't this really a norm? Well, because if I multiply a vector by 2, the number of non-zero entries stays the same, right? While a real norm, if you multiply by 2, it should also multiply by 2. Right? And so it turns out that many natural images are sparse. Of course, not in the pixel, right? So it's not like most pixels are black, except if you're doing maybe astronomy or something. But they are in certain bases, in particular in the wavelet bases. And this is exactly what JPEG 2000 exploits, right? If you take an image, if you try to save it, if you try to save it in a format that actually keeps the value of every pixel, like I think BMP maybe, or there's a few, you'll see that it occupies a lot more than if you use JPEG. And what they do is basically, JPEG 2000, what it does is it does a change of basis to the wavelet basis. And then in the wavelet basis, because natural images tend to be sparse there'll be a bunch of zeros. And so it just deletes away all those zeros and keeps the non-zero entries and their location. Right, and so natural images are sparse in a certain basis, but I mean, we can just assume that we're working on that basis. If the basis is known, then we can just assume that we're working on that basis. And when it's not known is a whole other problem, right? This is often known as dictionary learning. Okay, so let's define the set of sparse vectors. Okay, because we're going to take Gaussian widths, we want them to be in the sphere. So we take, they are in the sphere of n dimensions, such that zero norm is smaller or equal than S. Right, now, of course, differences like, differences of S sparse vectors, right? They are, which is really what we care about, they're just sparse vectors with 2S coordinates, right? So even if all I want to do is separate sparse vectors, I still care about keeping the norms of sparse vectors just where the sparsity is now double, right? So there's a bit more non-zero entries, but as we'll see, the Gaussian width will depend mildly on S in a way that is just, so I'm going to focus on computing the Gaussian width for the S sparse vectors, right? My goal will be to compute this quantity. But of course, if you want to actually be able to measure sparse vectors well, you would compute the quantity with 2S, right? You would just replace S by 2S, but of course, the calculation would be all the same. Okay, so let's do that. Okay, so we'll compute the Gaussian width, because this will tell us, at least if there were Gaussian vectors, the measurements will tell us how many measurements we need, right? Because M, the dimensionality that I'm projecting to, will be how many measurements you need. I mean, the key idea here is that we're not really getting all the natural images and then projecting them. Our measurement system is really projecting only the one natural image that we're seeing, right? And because it does not collapse any two natural images to any point, it means that the information I have about the natural image is enough to recover. It does not mean that I can do it computationally efficient, right? It could be that it takes, could be that there's no reasonable algorithm to do it, but that part we'll talk about next week. About what would be an algorithm to actually recover, right? So this I'll defer for next week. For now, we just want some kind of intuition of what's the scale of how many dimensions we need, how many measurements we need, and we're going to recover the scales from compressed sensing. Okay, so we get S smaller than N. You should think of it as much smaller than N, and we want to compute the Gaussian width of S sparse vectors. Okay, so what is this? Well, this is the expected value over a Gaussian vector in n dimensions of the max, right, of a vector, say X, that, right, its norm should be 1, its 2 norm should be 1, and its 0 norm should be smaller than S. Okay, but now if we think about what this is, right? What is this? There's X is going to pick a certain support of S points, right? Of S entries. It's going to pick a support and then it's going to maximize constraint to an L2 norm being 1. The inner product with G also only on that support, right? And so what we'll do is we'll get the norm of G on that support, right? Maybe I should just not have because I want to use the support of it later, right? So G is N0, right? Okay, so what is this? Right? You can pick the support of X. So it will be some subset of N, right? Whose size will be S. Okay, if the support of X is smaller, then just pick something that contains the support, right? And then you'll maximize the inner product in that support against that vector, where is G restricted to this support. But of course, if you maximize an inner product over the sphere, this is just the norm, right? So this is what we need to control, okay? Now, we know, if the support was just 1, it was about just finding the largest Gaussian, the largest entry of a Gaussian with n independent Gaussians. We know this is around square root log n. And essentially what we'll see is that the right value for this will be around square root log n over s. Okay, so let's see that. Okay, so we're gonna do the the tool that we've used many times. We're gonna do union bound, right? So we're gonna first fix the support, right? If you fix some support, you have from this inequality on chi-square random variables that we saw earlier in the class, we have that, that if we fix the support, then the norm of this is just squared. It's just the sum of S, the square of S Gaussians independent. And we know a lot about it, right? In particular, we know its tails, the probability of being bigger or equal